So our next reaction with amino acids is going to be called reductive amination, not animation as the Walt Disney cartoons, right? Amination, not animation. Okay, so what is reductive? Well, okay, if you take a look at reduction in organic chemistry, you're reducing the number of C to O bonds. This is a common trend that we've always seen. Oxidation reactions, reduction reactions. This is a reduction. It reduces C to O bonds. So that means we're going to start off with a molecule that has maybe a certain number of C to O bonds, and then we're going to reduce those number of bonds after a series of reagents and the reaction takes place. So what kind of things do we start with? Well, typically we start with what we call an alpha keto acid. Okay, so acid is going to refer to the carboxylic acid again. Alpha means on the alpha carbon, and it says alpha keto acid. So alpha keto acid is what we start with. On the alpha carbon, we have a ketone group. And then off of this, we can find any other kind of alkyl group that we want. So let's just say that we have a CH and a CH3 and a CH3 group here. Okay, so what reductive animation will do is that it will take this alpha keto acid, that's what this is called again, right? So alpha carbon, and then keto is the ketone group, and acid is a carboxylic acid. And we are going to react with it a couple of reagents. Number one, we're going to do excess ammonia again, just like we did in HVZ. There's really no difference there. And in number two, we're going to throw in some hydrogen and palladium. Now, it's not uncommon to put some trace acid here as well, so don't be surprised if you see that either. So ammonia and then hydrogen, and this will reduce the number of C to O bonds that we have. Now, this is an alpha carbon, so the alpha location is going to be very important for us. We don't really want to destroy this. We want to keep that kind of carboxylic acid intact. The only thing that we want it to do, if it's going to do anything at all, is to lose the proton. So we can do a COO minus. That's actually how we've drawn the amino acid structures this entire time. So if that can just simply lose a hydrogen, it's okay. But we do not want to destroy the C double bond O at that location. Alright, so what happens here? Well, the C double bond O and the O kind of stay in place. This gives us the acid part for the amino acid. And at the alpha carbon, what we see is a substitution reaction in a way. Not really. We break the double bond and then the mechanism goes forward a couple of other steps. But eventually we end up with an NH3 group here, just like with the HVZ reaction. And then the remaining part of this amino acid will stay the same. So it's still a CH group that's attached, and we have a CH3 group down and a CH3 group over. Alright, so this part of the molecule did not get touched. This is our R group, right? So here is the R group on the amino acid. This is the alpha carbon, this is the acid part, and this is the amino part. So amino, carboxylic acid attached to the same alpha carbon. This is a chiral carbon because the fourth group is this isopropyl group. And this is how we make another version of an amino acid. In this case, I started with isopropyl as the R group. It makes this kind of V structure at that location. What I have made here is valine, V-A-L and V for 3-letter and 1-letter abbreviation. So congratulations, people. You just did your reductive amination reaction. It's as simple as that. It's very similar to HVZ. The only difference, it even uses excess ammonia. So they both use the same general reagent. The only difference is what else follows. So in HVZ, We start off by putting bromine on the molecule and then replacing that bromine with NH3. In this example, the mechanism's a little bit different, but you still see excess ammonia there, and this time you see some hydrogen and palladium that are involved, so that will help the reductive part of the mechanism go forward. So there is the makings of an amino acid. So the take-home story so far is that there's two ways to make an amino acid in a laboratory. Now, your body makes amino acids in different ways. They don't really have little laboratories that have excess ammonia and hydrogen and palladium in them, but they do them in a different mechanism route with the help of enzymes and that type of thing. We, on the other hand, we don't really have that kind of opportunity in a laboratory environment. So this is the way that we make them in the lab. Two ways at least, and in the next video we're going to take a look at our third way, which is a mouthful, and I'm going to save off for that until you start watching the next video in the first couple of minutes. We'll talk about the naming and we'll talk about what happens. But this is the reductive amination. We now have talked about HVZ as well. So two ways so far to make amino acids. Just like in the previous one, this R group is very important because this is what you change, because when you change this, this is how you get different amino acids, right? All of the amino acid structures, this part of the molecule stays the same. So this carboxylic acid, alpha carbon, and the amino group, this doesn't really change from amino acid to amino acid. What's important here is this R group that you're choosing. That is what's important. So that part gets changed, and that is how you make different amino acids. So it's all about what you start with there for both reductive amination and the HVZ reaction. Okay, so we'll stop here. Pretty short lecture, at least on reductive reaction, and then in the next video we'll talk about our next reaction on how to make an amino acid. So stay tuned. We're not yet finished with the reactions, but the good news is that after one or two more reactions, that's it of this lecture. So there's only really 4, maybe if even that, for you to know and take to heart.